Go.
Okay, so this is the block and tackle, and I had assembled this yesterday, and then it fell apart on me, and you would have to keep in mind that that easily could happen to you too. So now I'm going to take it apart again in order to put it back together. Okay. All right. I just do this here on the table to, and then you see that I have to do all of this here to find the beginning of this whole thing. And then I make a knot. Great. And let's stop the camera because you don't need to. Alright, so of course you didn't need to see how I got rid of the knot. So I'm going to string it over here, and I know that this won't slip. You might have slightly different pulleys, so this might be a little bit different for you. I think my pulleys are a little bit easier to handle with because they're open on one side. Okay, one important thing to point out as you put it together is always keep it under tension, because if you don't, then the hauling part, which is the lower pulley, will actually unravel on you and the string will come off. And of course, I shouldn't be talking too much and rather focus on this. All goes well, I'm almost done. Now, I actually ran out of sheaves here, so I'm just going to put it over this one here again. And in order to keep the tension, put it on this counterweight for now. And here we go. Alright, if you could come around and film kind of like here, this part would be cool. Okay, I put on 1 kilogram right now. Respectively, I'm going to put a second one on. I have to think how I did that. Yeah, I think that's the way I did it. Keeping the tension. Everything falls apart on me, then I guess I didn't keep the tension. There we go, hopefully. Okay. Alright, so now I got 2 kilograms on here. And I have 9 strings holding it, so 4, 4, and another 1. So 9 strings are holding it, which means that the force with which I have to pull should be only 1/9 of the weight that I have on here. I have 2 kilograms, which is roughly 20 newtons. Divide by 9, and I'm back to a little bit over 2 newtons. That's what I should measure. However, of course, I have friction in here, and I also have to pull the lower pulley up. I should be measuring more than a little bit over 2 newtons, and that's what I'm doing here. And then when I do that here, again, keep the tension. I'm going to hold on to this because I don't want it to just totally fall apart here. And then I'm going to pull here, and here we go. If you could come over here and try to film the numbers on here on the spring scale, and from my angle I want to say it's 3.3 newtons what I'm measuring. You kind of see that too?
Mm-hmm.
Okay, so and then you would pull and pull it up 1 meter, and of course I have 9 strings on here, which means that I would have to pull 9 meters in order to haul it up that 1 meter. I'm not going to do that now. It's just a demonstration for you. You would actually have to do that, pull the entire 9 meters. Okay, at this point here. Again, I don't want to lose it just in case I have to retape something. I would be actually done. What you would do is you would start out perhaps with 7 strings or 6 strings, whichever you're gonna do. If you do the odd ones or the even ones, that means even number of strings or odd number of strings. You get, if you could come around here and film here, you get an odd number of strings if you tie it. If you start tying it here, you get an even number of strings if you start tying it there. And then you would start with, let's say, 7 strings, and you would go down to 5 and a 3 and do all your measurements. And I think with that I'm actually done.
This is the analysis for the example data, from my example data for the block and tackle, and I'm first going to grab the equations that I need. Again, I have just posted these here in one place for student use, so that I only have to edit it in one place if I need to. There we go. And now, because I'm looking at the block and tackle data, I can move this over somewhat. There we go. Okay, I used 2 kilograms because it was so exact. Because I used regular lab weights, it was pretty much exactly 2.00 kilograms. That means the weight of that load was 19.6 newtons. I multiply by the acceleration due to gravity of 9.8, so 2.00 times 9.8 is 19.6 newtons. I was going to lift it up a token height of 1.00 meters. You see that in my experiment I didn't do that, but I just want to use it as a demonstration. I just didn't want it to fall apart on me while I'm doing this demonstration. You would have to pay attention to it because you're going to have really a 1 meter length in each of the strings that you have on there. Okay. The other things that I measured was that I had 9 strings that were supporting the lower pulley, that is the hauling part, and the rest, which pretty much was measured, respectively calculated. Okay, so the work without the pulleys is the lifting work here, which is multiply the force of 19.6 newtons times the height of 1.00 meters. So of course I come up with 19.6 joules. Number of strings is 9. That was supporting the lower pulley. The expected effort force is, I'm going to get this here to the next line, it's easier to see, is the load, the weight of the load, divided by the ideal mechanical advantage. So 19.6 divided by 9 comes out to around 2.2 newtons. So I should be measuring 2.2 newtons when I attach the spring scale to the hauling line and pull on it. However, as you will see, or as you saw in the video, I actually measured 3.3 newtons. Oh yeah, I guess I should have put that in earlier because I already measured it. So I measured quite a bit more, but that of course is the friction in the string, between the string and the sheaves, as well as pulling up the weight of the lower pulley. Still, I have quite a bit of a mechanical advantage, and that of course is the idea of a simple machine. Let's actually determine this one here first. Hauling line distance. D is, of course, I have to pull it up 1 meter, but I have 9 strings supporting it, and each one of these needs to be pulled up 1 meter, so the hauling line has to be pulled a total of 9.00 meters. That's pretty much exact because this one is an exact number and this one here was a token height of 1.00 meters. The amount of work that I therefore expended is written, let's see, right here. So the amount of work is the moving force 3.3 newtons times the hauling line distance of 9.00 meters, so that comes out to 29.7 joules. When you compare this one here to this one here, these two should be equal if it was an ideal simple machine, but again there's friction in there and you have to pull the weight of the lower pulley, so that's why actually the work here by using the pulleys is actually more. But of course the reason why you still do that is because you have that mechanical advantage. You have to exert less force, in this case of course the actual measured force due to friction and the weight of the lower pulley. So therefore the actual mechanical advantage comes out to, that's written here, divide the force of the load, the weight of the load, by the actual measured force, 19.6 divided by 3.3 comes out to 5.9. Again, no units because I divide force by force. So that means that I still reduced the force by approximately a factor of 6. The efficiency is written here as the lifting work, 19.6 divided by 29.7 joules by using the pulleys, and that comes out to 66%. So 100% would have meant that I used the same amount of work either way, with having a certain mechanical advantage. And of course I don't get a free lunch, so it has to be 100% max. But by using the pulley system, the block and tackle, I have an efficiency less than 100%, appreciably less than 100%, which means I actually expend more work. And of course we see that right here, 29.7 compared to 19.6. But I'm willing to exert more work because the force that I used in order to pull that was appreciably less than that of the force. But of course, again, I don't get a free lunch. I actually had to pull more string than actually the object was lifted. Okay, that was the analysis of my example data for the block and tackle.